To send humans to Mars, we need a revolutionary rocket technology. This is the Saturn V rocket that launched astronauts to the moon. It is the largest rocket ever built, larger than even the Statue of Liberty. This rocket requires an enormous amount of fuel in order to launch this relatively tiny spacecraft into orbit. And from there, it requires even more fuel to get the spacecraft to the moon. As you can see, traditional rocket technology is not very fuel efficient. So how do we get to Mars, which is 200 times further away than the moon? The answer is an ultra fuel efficient technology called electric thrusters, or plasma rockets. By replacing the old rocket technology on the spacecraft with a modern plasma rocket, this spacecraft can get to the moon with 1/10 this tank of fuel. Or seen another way, this tank of fuel can get you to Mars. So why haven't we gone to Mars yet? Well, this thruster must operate for many years for a Mars mission. Imagine what would happen if you left your car running for a few years. It would break, and so will your plasma thruster if you run it long enough. So what's the solution? Make sure it doesn't break. To do this, we have to understand how a plasma thruster works. The thruster creates a plasma, which is a soup of positive particles called ions and negative particles called electrons. These ions are shot out the back of the thruster, pushing your spacecraft forward. Simple enough, right? But what happens when this plasma gets close to the walls of the thruster? When an ion hits the wall, a piece breaks off. And if enough ions hit the wall, eventually the wall will completely break, potentially causing your thruster to explode. But what if there was an effect where the pieces that break off turn around and go back to the wall, repairing itself? Could something like this actually happen? Turns out, yes. This effect, called plasma redeposition, can magically repair the walls of your thruster, making it unbreakable. For my research, I created plasma and smash it against different types of advanced thruster wall materials in order to maximize this plasma redeposition effect. So far, I've found that I can double the lifetime of current thruster materials. That can make the difference between getting to Mars and getting stuck halfway. My end goal is to design a thruster that can last 10 times as long, making it effectively immortal. Such a thruster would solve the fuel inefficiency of traditional rockets and enable us to travel to Mars.